Welcome back to Beyond the Patterns. So today we have another invited talk in our series, and it's a great pleasure to welcome Professor Dr. Mauricio Reyes from the University of Bern to our lab. He will be giving a presentation entitled Medical Image Analysis in the Era of Deep Learning, from Performance to Challenging the Alchemist Within. Professor Reyes conducted graduate studies in electrical engineering at the University of Santiago, Chile, where he was awarded the Best Electrical Engineer thesis by the Chilean Institute of Engineers School. He conducted postgraduate studies to obtain a Ph.D. in computer sciences with a specialization in medical image analysis from INRIA, France in 2006. He is an associate professor at the medical faculty of the University of Bern and is currently leading the medical image analysis group at the ARTORG Center for Biomedical Engineering Research at the University of Bern. His research focuses on basic and applied machine learning methodologies, as well as biomedical engineering solutions to improve healthcare throughout medical image computation technologies. A particular strength of his research has been the emphasis on developing solutions that are designed to be integrated into the clinical workflow. Dr. Reyes has participated in several Swiss National Science Foundation projects, Commission of Technology and Innovation projects, EU FP7 projects on computational oncology, computational anatomy, and further projects supported by Swiss foundations. From 2006, he has secured over 7.6 million euro research funds. He has an H index of more than 30 and authored over 230 articles with more than 6,000 citations. His entrepreneurial work has also led to the creation of one consolidated company, and the second one is in its first steps. So it's a great pleasure to welcome Mauricio here. And Mauricio, after the short introduction, the stage is yours.
Thank you very much, Andreas, for the kind invitation. Thank you, everyone, for being here. I'm from home. This is my virtual background. This is, in case you haven't been to Bern, this is the main building of the University of Bern. It's a nice campus. So when you arrive with the train, on the upper floor, there's this nice campus. So in case you visit Bern, it's a small town. It's a very nice place to come. So you are most than welcome to our university, to our laboratory. And yeah, so I wanted to show you some of the experience we have on working with deep learning for medical images, and the challenging the Alchemist within comes from some of those challenges that we have many times every day while working with these systems. So as an intro, I want to first show you some of the systems that had received first FDA approval. So what you see here already in February 2018, April 2018, first systems, or among the first systems receiving FDA approval. And this is just to sort of motivate the power or the importance, the impact of AI technologies in our society, in our technologies, even to the point that FDA itself has stated that they want to change their way of proceeding with FDA approval to facilitate and to profit from these technologies. So now, related to this, many times we read many articles about deep learning methods, results, and there's one article in this sense that I want to show you. That is this study. You see Eric Topol, Hugh Harvey, and other known researchers. We have a strong clinical emphasis, and this paper is about AI versus clinicians. It's a very interesting paper in case you are interested in the translational aspects that talks about this review they perform on the design, reporting standards, and claims of deep learning studies. So many times we focus on the methods, and here one of the main messages is we need to also focus on the way we evaluate, the way we actually look at the results, and we prepare the experimental design to evaluate our systems. One of our main areas is in brain oncology. So here we have seen from the standard machine learning to now deep learning, how this has contributed to our work. So what you see on the top left is basically a system that performs brain tumor segmentation. This software is available. It's called Bratumia. It uses very classical machine learning using decision trees that we've been using for many years. Now we are in beta testing to release the deep learning version of Bratumia. We call it Deep Bratumia. That takes 4 sequences. Normally you need 4 sequences, MRI sequences, to perform then the segmentation of the brain tumors. And on the right, you see a segmentation of organs at risk. This is very important in radiation therapy planning. And these delineations need to be done for every patient. And this is part of the planning. And this is all organs that need to be spared from radiation. So you can imagine the time-consuming and tedious tasks that hopefully a computer can replace. What you see on the bottom left is an overlay of these segmentations on an industrial system, commercial system that's used for brain tumor biopsy. And so here is the idea of enhancing the information by overlaying the brain tumor segmentation on top. And what you see on the right is a longitudinal analysis for patients. So typically you have a pre-op, an immediate post-operative, and then you have time points that you can see on the right, these curves. The colors correspond to the different compartments of the tumor, and the enhancing part, so you see the active part, this is one of the main areas of interest for clinicians, and clinical protocols used to assess the disease are also based on this, on the volume or the size of this active part of the tumor. So you can see the complexity of the task. You have 4 sequences, volumetric sequences, and then you have time points. A neuroradiologist needs to go back in time, define a starting, what we call the nadir point or baseline, and then start deciding, is the tumor progressing? Is the tumor responding to therapy? Is the patient stable? So it's a rather complex task for them. So this is what our hope is, to help them with these technologies. Now, in our research community, one of the initiatives that have grown over time is the BRATS competition. And so this is the brain tumor segmentation. I wanted to show you first the standard machine learning results we used to see in the past. So this is a box plot display of dice. So a low dice is bad. You want as high as possible, maximum of 1. You see on the left, these are the inter-rater variability. So inter-rater, this is rater to consensus, and this is the rater to rater variability, sort of worst case scenarios you see there. And then in colors, you see the computer results, and you see that there is a difference, right, between humans and the systems. You see a lot of variance in the results, so the robustness of the systems is not really similar to the humans. You would like computer results to sort of always be in that green area, right, where this is the rater where humans normally perform. And you would like to avoid any computer result that goes in that red zone. So now that was for the first years of BRATS, when we were using decision trees, SVM, and other classical standard machine learning. When deep learning arrived around the year 2014, we saw the first approaches. We saw that improvement. And the next plot I'm going to show you is a summary, a very nice summary from my colleague Bjorn His, who summarized the years 2012 through 2017. and its rank. So you see again on the left, the best, the top rank, and then on the right, the bottom part of the performance. Now, you can see already that there is an increase, so we are getting better. The variance is also getting better, so it's reducing. When we zoom into the top, we start seeing very interesting things. So let's zoom into the top. And we see here the human performance. And this one over here corresponds to the fusion of experts. So when we take all experts and we fuse them, we call that the reference. It is anyways a gold, it's not a gold standard, it's sort of silver standard because they have errors. And by means of fusion, we reduce those outliers, those errors. We can do the same with computer results. And those are the box plots you see in yellow. So when you fuse the deep learning methods, you start also gaining performance. Now we have seen we have tested in other areas like a stroke, and the performance gain is present, but not as drastic as we have seen in brain tumors. Here, doing a fusion of methods is actually a good idea. We see now 3 human raters. So you see this one here, and this one here. This fellow here, it took him more than an hour and a half per case to really delineate very carefully each case. Whereas the other 2 were working in a clinical setup using a semi-automated system or spending half an hour, 45 minutes per case. It's still time consuming, but it's closer to the clinical reality. So, and you see that computer results are getting closer to that. And we could see, well, now it seems that the task is done, right? It seems that we have solved the problem and we just move on to the next one, right? So this is what I like to present, what's the catch? Are we actually done? Are we in that level of accuracy? And here where come some of the issues that I want to focus on the rest of the talk. The robustness issue is one problem. So I want to show you now the same analysis, now including 2 more years of the BRATs. So from 2019 summary, where we started also looking at more of the outliers we see. So in this plot, you can see that there is quite a large number of mistakes that a doctor would say, well, that looks like a computer result. That's something I wouldn't do in practice, right? So that's the issues we are seeing, that we are identifying. And here comes now in the title of the talk, the Alchemist within. Because many times we achieve a level of accuracy, we are happy with it, but in many of these work, we need to do a lot of trial and error, fine-tuning. There are all these tricks, right, that we exchange with colleagues in a conference, like when do you change your laws? How do you check the weights when you get stuck in your validation? How do you do a transition on pre-training? And all those tricks, right, that we all have heard or we use. Many times the system works, but we don't know exactly why. Or we have an idea, or we have maybe even a misconception. We don't know, right? But we are very happy that when it works. Many times we get that bad result and we have problems. We struggle to explain it, to say, well, I didn't expect this bad result. Or sometimes the worst scenario is when it works flawlessly, but it works due to wrong reasons. And I'm going to show you some of these examples. So on the right of the slide, you see that there was actually 3 years ago an interesting debate when Professor Rahimi was awarded at NIPS. And in his award speech, he was saying that machine learning has become alchemy. And LeCun challenged that opinion. And here, I don't want to say that we are alchemists, but I think it's a natural progression in the field. Normally, the theory is catching up with the practical aspect. And I think that in this field, those practical aspects are coming very rapidly. We are understanding new things or ways of doing, and the theory is catching up, and it's very solid. But there is that gap that sometimes make us struggle when those errors happen or when those systems behave in an unexpected manner. So I invite you to read the post. It's actually very interesting. I didn't know about it while preparing the talk. I saw it, and it's an interesting read. So now I want to focus on three aspects that are connected to this. The first one is robustness, the problem of robustness, and then uncertainty as a potential mechanism to assist in that problem of robustness, and then interpretability, mechanism to actually understand or have a bit of more understanding or reasoning of regarding computer results. For the robustness part, I like to first motivate it by one of a very important area of research, which is the utilization of omics data. So probably you have seen all these genomics and epigenomics and proteomics, and the hope that by accumulating this at a patient level, we will be able to pass that inflection point that would lead us to a very personalized medicine where we can do much better on treatment, on healthcare in general. Now, what's the take for imaging and omics? So there's actually a new, we call it a new omics in town, which is radiomics. And what you see here is a very nice presentation from my colleague from neuroradiology, Professor Roland Wiest from our hospital, who has this type of data, in radiomics data. So this is actually a batch of sequences, MRI sequences, available for one patient. So you can see before I was showing 4 sequences, but there's actually more, right? Resolution is improving. We have more data to actually digest and mine. And there's where the promise of radiomics, the analysis, the data mining from pixel data comes as a promise for healthcare. So in radiomics, one of the main aspect that had been discussed and researched is the use of texture, the information that texture has in medical imaging. In the case of tumors, particularly, vascularity of tumor is many times measured through texture and metrics that show us the progression of the vascularity of the tumor, and it's connected to the aggressiveness as well of the disease. I want to show you now a parallel paper that was published, a very interesting one. I advise you to check it if you haven't, from the University of Tübingen, where they were analyzing, and their main finding is that CNNs are biased towards texture. So here they did an experimental design where they were removing information, and one can see that as the information is removed, the performance of the systems of very popular networks are dropped quite substantially. Whereas when you only provide textual information, the system can be quite confident about what the content of the image is. So this shows us that there are some particularities. There are this type of information that networks seem to be quite interested in. So for us, texture in medical images, we do that connection to disease progression, to diagnosis. So we are interested now in knowing what happens with that textural information, or that even radiomics information across different vendors, because in reality, we want systems to generalize over different protocols, over different vendors. So this is the Ph.D. work of Yannick Suter. And on the left, you see typical vendors with different strength fields, and there are different protocols, even different models, right, of the same vendor. You will have differences. And then there's the whole user, the person, the technician that defines those protocols that can introduce differences in our imaging information. So here we have questions like, are radiomics features robust? Are all feature types equally robust or not robust? And we tested this in the problem, the task of survival prediction in glioblastomas, GBM patients. So one of the basic and very simple ways of analyzing robustness of a feature is by means of sensitivity analysis. So we designed perturbations, and what you see here is perturbations based on inter-rater variability. So in radiomics, typically one of the steps is delineate the object of interest and then extract information from those areas. So the inter-rater variability is the question, how does this affect the different features, signal noise to ratio, case-based subsampling, isotropic resampling. When we work with texture metrics, typically you need an histogram, therefore the bin size plays a role, and also slice spacing that also varies, it changes across protocols and vendors. So we define then an experimental design where we said, well, typically one would train data on a single center. So you have your local hospital, you collect your data, you create a model for a task. Then you would like, and you hope that that model generalizes when you distribute, you pass it to another colleague in a different center using different data. So from single to multi-center. So I'm going to show you now the pipeline, and we're going to go through it. Basically, the green part is basically your single data analysis, and the blue part is your multi-center where you want to evaluate performance. Now, we divided the single-center data into a subset. One on the left side, this is where we actually created all these perturbations. So you see this all set of perturbations, 125 perturbations times 4 sequences for the different tumor labels. So we have 3 tumor labels typically, and the number of features provided. In this case, we use the PyRadiomics framework library to calculate all these features. So that led to about 16 million tests using perturbations and all these combinations. We use the correlation coefficient as a measure of robustness. So the higher, the better. And then we selected robust and predictive features from this set. On the second subset, we actually look into a reduction of features. So we wanted to reduce features to avoid the curse of dimensionality. And then we also look into what would be the best model for those combinations of features. So that's the best performing feature and classifier performance you see here at the bottom. And that's kind of the best that one could do by combining good features that are predictive, that are robust, and the model that goes along that provides a good performance. And then we perform that, we tested that model with those features in our multi-center data. So first we analyze the robustness of feature per category. So in bioradiomics, for example, you have different types, texture, shape, first orders, statistics, and so on. So let me show you now with spider plots how we analyze the robustness. So a typical spider plot looks like this, where you have a different type of perturbation, and each point here corresponds to the ICC value. So the closer to 1, the more robust that feature would be. And then you see per color is the family or the type of feature. So you see first order statistics, you see GLCM, that's a texture type, and shape. We also look at, this is from a radiology paper where they propose looking at the diameter of the tumor, centroid, and then also we look into deep features. So these are features created from a neural network, and we analyze the feature robustness. So overall, so one of the findings is that the texture-based features they have problems. They are not so robust. For example, beam width, slice spacing they tend to actually create a lot of troubles in terms of robustness. Whereas the shape of the tumor are way more robust, as expected as well. The data doesn't change that dramatically. Deep features, they are kind of in between. We realize that they are not super robust, but they are also not that bad. So you can see that in terms of robustness, they tend to be more sensitive to voxel size and iterative variability and slide spacing, but less to the other aspects. So this is an important message, we believe, because we in the community we really look into the texture information, and there are many publications looking into the importance and the predictive value of these texture-based features. But there is the problem of robustness that we have reported here. Now, the question is, what happens when you do that trade-off between saying, I'm going to sacrifice some features that, although they are predictive, they seem not to be very robust? What's the trade-off in terms of now performance of AUC in a classification task when you're saying, I need to classify these patients by the overall survival in days, and I want to compare what happens when I go for accuracy and performance versus what happens when I prefer robustness. Do I sacrifice accuracy? And that's what I'm going to show you in the next slide. So we ran here two types of experiments. Single center are the light color bars, and the multi-center is on the darker. Now, the color itself corresponds to the non-robust. We call it non-robust, no prior. So this is, you go for performance, you go for accuracy, and you don't care about robustness. And robustness, then you have this, we have two priors, one clinical, where we ask our clinicians, what do you see in the images, or which sequences do you use to estimate survival of that patient? And they said, well, T1C, that's the contrast enhanced sequence, and the flare sequence. And so we just focus on features coming from those sequences as a clinical prior. The idea here was, let's use any kind of prior we would have to reduce and fine tune those features. And then our robustness prior, we call it handpicked, where we analyze based on what you saw before, which features are more robust. Now comes the analysis of AUC. So the light blue bars correspond to what you would get during single center training. And the values are really nice, right? They're all high. When you go with that model into a multi-center, you would drop to the dark blue bars, here or here, here or here. So you see that drop performance, that's relatively high performance drop. When you then say, well, I'm gonna add my clinical priors, you start seeing increments. And even when you go for a robust data-driven analysis of the features, you would actually gain. So that was an interesting finding. We were thinking that we would actually sacrifice performance over robustness, that at least our result would be constant. We would have that like good and bad result, but here we would have something lower. But we found out that robustness actually can even help in performance. Overall, my personal opinion is that doctors would always prefer a robust system than a super accurate system that can sometimes just fail dramatically. So that's one aspect of robustness. So in summary, not all features are robust. Texture-based features are less robust. So we need to be careful when using them. We need to look into the normalization. We need to look into the data of source and analyze that aspect. And finally, robustness, actually introducing robustness into the selection process of features can actually boost performance when deploying a system and to make it more generalizable. The second part I want to show you is about uncertainty. And this is the PhD thesis of our student, Alan Jungo. And here we have the questions like, can we improve segmentation and downstream task by incorporating an extra piece of information? So these uncertainty maps that you can see here at the bottom, they pixel by pixel, one can estimate the certainty or uncertainty of a computer result. So the question was, can we use that to improve segmentation results? Can we use it to reduce effort of clinical experts by sort of automatically changing results or correcting based on those uncertainty maps? And finally, since we are moving the problem of saying to a doctor, check the results, the computer might be wrong, into the computer might flag based on those uncertainty maps, which cases might require attention. Therefore, the question is, are those uncertainty estimates reliable enough? So for this, we had to look first into the ways to calculate uncertainty. And here there's a field by itself now where there are different ways. And what I'm presenting here are the most popular ways that are people using for uncertainty estimation. And so one is Monte Carlo or concrete dropout. So you can see here in the schematic that per layer one drops connections, and that generates a variance in the output. And by measuring that variance, one can have an estimate of uncertainty. Concrete dropout is basically there is an optimization that optimizes that dropout rate for you. Ensembles, that's also a popular way where we have different models, and basically then you need to aggregate those results to have an estimate of uncertainty. Test time augmentation is where you actually perturb the input and you measure the variance in the output. And there is also the aleatoric uncertainty, where here you have an extra output in the network that assesses the uncertainty in the input. So these are systems that can scale well with data, compatible with existing and complex architecture. So they are very nice. They are really sort of straightforward to use. Now, let me show you what happens when you use Monte Carlos. We took Monte Carlos one example, Monte Carlo dropout, and we use it on this estimation of range more segmentation. And you see things like this. So you have your input image and the flare overlaid with the segmentation result. And you have uncertainty maps depending where you are performing the dropout. So at the center, over here at the end, or as a full MC dropout where at each layer you are doing dropout. So we see that the maps, they tend to change. So this one especially is more distinctively different than the others. The segmentations, they do have some differences. So the question we have is, can we actually gain from using those voxel-based uncertainties by, for example, swapping labels of those very high uncertainty to see if we could make corrections? And we found that that was not really reliable, was not working. So then the question was for us, we cannot sort of automatically use the voxel-based uncertainty estimates in segmentation to reduce time and efforts in the corrections. It doesn't seem reliable. And so we look into the calibration part of the models that were trained. So for that, we also added a second data set. That's a melanoma, skin melanoma, the ISIC. It's called the ISIC. So I'm going to show you now calibration plots for the BRATS data set and for the ISIC data set. And first, I'm going to show you what happens at the data set level. So you see that you would like to have a 45-degree, a diagonal line, or a well calibrated. At the data set level, you do see that. And this is for different, at the bottom, you see the different type of uncertainty estimation methods we tested for both data sets. So if one is interested in a population-based analysis and wants to use uncertainty, the data set level calibration seems to be okay. There seems to be a good calibration. But when we start looking at individual cases, we start seeing underconfidence, overconfidence, but also well calibration subject. So then the question or the issue comes that clinicians, they want to work at the population, at the patient level, sorry, at the patient level. They want to use this result on a patient level. And there we have the problem that depending on the model and the patient, we would have a overconfidence or underconfidence. And we think that this is one of the reasons that leads to a unreliable use of the technology currently at the patient level. Now, something that has been also shown, that we shown 2 years ago, and that's now it's also shown by other teams, is that we can actually aggregate the voxel-wise uncertainties into one score. So rather than saying, please check this voxel or these areas, we say, please check this volume, as it might seem to have a problem. So we propose something very simple at middle 2018, where we aggregate these uncertainties is what we call a doubt score. So should we check it or not? And the approach is very simple. I'm going to show you. So we have our 4 sequences. We tested this on resection cavity. So this is post-operative images. And you want to resect the amount of the cavity here, which is very important for radiation therapy. The aggregation method is very simple. We realized that uncertainty is always happening at the border, right? So, and as we move away from the border, that uncertainty values might be spurious. So we use first a distance map combined with a mask, that's a threshold, basic thresholding of that, to then aggregate these results in a weighted manner based on that distance map. So by doing that, we actually we try to increase the robustness of the aggregation process into a very simple doubt score. Then one can, in a population, one can get those scores and use it as a threshold of should we check that case or not. So let me show you what we found in this study here on brain tumor resection. So that you have the dice on the horizontal and the doubt score on the vertical. The numbers correspond to the use case, and each point corresponds to a volume of patient. And a typical OK segmentation dice value would be in the area of 0.75, 0.8 for this task. And it's in the area of the inter-rater variability. So you could then divide bad segmentation from good segmentation. Then we were interested to know what happens with our doubt score when, for example, we set a threshold based on either a validation set or an experimental value that we decide based on an external set. And for example, based on that threshold, we will have these 4 quadrants. And you would have then cases that I'm showing you here. So for example, this would be a good segmentation, and the doubt score is saying these cases should be checked. So this is a false positive. And when we look at the images, we see that there is uncertainty due to the cropping of the image. So this is a confounder effect that is actually also affecting the doubt score. We see good cases where there is a bad segmentation and the doubt score says, yes, there is a problem here. In this case, we see that the segmentation is rather poor and there is uncertainty shown. On this case, we have good segmentations and no expert review is needed. So here we have the case where there is no need for the expert to review these cases. And then we have these other cases where there is a bad segmentation and there is no expert review needed. So this is the worst case scenario, where we also found that the uncertainty estimates are very much linked to the performance of the segmentation model. And that's a bad feature. So that the better the segmentation, the more reliable the uncertainty. And that's a link that you would like to decouple. So many teams now are investigating approaches where you decouple your uncertainty estimates from the segmentation performance. So in that direction, we are moving as a collaboration work with the European Organization for Research and Treatment of Cancer, EORTC. We went for that idea of training a system that, given an input and a segmentation, we would like to have a score, a predictor that tell us if that should be tested or not. So when training as such a system, such a predictor, we see that the data is quite unbalanced. So there is a bias here in the data. And this happens naturally because most of the segmentation results are okay, are good, especially those from humans. So one way of that we found is to bring balance to the data is by using a variational autoencoder to simulate, to do data augmentation and simulate that set of data sets that brings that balance. And therefore then the model can be trained and a better prediction of dice could be used, could be obtained on testing cases. So these are current efforts from our team to bring quality control in the systems. The third and last point I want to go quickly is on interpretability. And I want to start with the definition of interpretability. There are many, but one that I like the most is understanding the link between features used by machine learning and the prediction itself. Now, why do we need interpretability? In medicine, there are many good reasons to desire this: accountability, trust, quality control. We have seen this before, ethical aspects, and simply data exploration. We want to find biomarkers and we want to understand what these systems might be using as data to drive decisions. Now, in the literature, probably you have seen type of studies like this one, where people have reported that it's rather easy to fool networks based on particular perturbations. We talk about the work of Tübingen on the textual bias, and this one recently, where they recognized that the system was actually learning to find areas in the images to boost the performance, but these areas have nothing to do with the disease or the condition itself. So for that is where in interpretability, one of the popular areas of research is saliency maps. So identifying the pixels that drive decisions. This is from one approach called LINE, where you can see, for example, an original image being classified as an electric guitar, an acoustic guitar, or a Labrador. So this makes sense. Those are areas that are driving the decision. The approach itself is very interesting. Due to the time, I won't go through it, but I invite you to check it out. And here's an interesting case where there was a bias in the data. It was purposely induced to try out this effect that this data, there was always a link between the snow and the object that needed to be recognized. So the system learned to actually recognize the snow to classify the image. And you can see here, this is the explanation for that Husky classified as well. And here comes the clinical example where we see that the system learned to find out that marker. So these were patients in an emergency room being imaged with a handheld device. And the system learned to identify that. And that's kind of a local minima in terms of optimization that the system said, if I find that, I can boost my classification accuracy. And so you can imagine that's not that easy. If things are actually working, if you have an AUC of 95% or more, it might be tricky to recognize that there might be a problem behind. And here, saliency maps can be very interesting. So since now 2018, we've been organizing a workshop at MICAI. This is our main venue. We call it iMimic for interpretability in medical image computing, and where we talk about these issues. And I'm going to show you now a short video. In the first part of the video, was a promotional video for the iMimic workshop. You see different people from the community, renowned people that talk about it. The second part was more of the fun for us to promote this initiative. So enjoy the video.
I think it is difficult to appreciate just how far artificial intelligence has advanced and how far it is advancing.
AI. I think that's just gonna unlock so much potential in so many different domains.
I resent right now that the neural net wave and the deep learning wave has become so predominant that people say, well, that's the way to go. You just collect data and intelligence will work itself out. And that's just not true. I don't believe it.
There are many settings where a deep model trained on enough data that exhibits enough accuracy on test data is all you really need to go, and you don't need to be able to see what's inside that black box. However, there are other settings where that's a very risky thing to do.
Gain insight. Once that insight is gained, then start applying rules and regulations.
In 2016, Europe passed a new omnibus piece of legislation called the General Data Protection Regulation. Europe treats data protection as a fundamental right, and GDPR is a big deal. They were worried about automated decision-making. If the explanation is not possible, then either you can't use the technique or you do so at your own peril. At a certain point, the law is the law.
And we just find that every time we put on this magic glasses where we can see what's inside the model, we find an amazing number of things that are wonderful, but we also see things that are very surprising, very disturbing. And it's just so important to be able to put on the magic glasses in many domains and see these things before you deploy. And then help you try to understand what's in it, open up the black box a bit.
So the iMimic workshop is continuing. We really hope that we can repeat this next Mikai. iMimicworkshop.com is the website. There is material, and I invite you to browse the material and contribute if this is an area of your interest. The next part that I would like to mention to finalize is some of the examples. What happens in medicine with these approaches? So first, I want to show you an example where you have a classifier of low-grade gliomas versus high-grade gliomas. And the question was, what is the system using to classify the image? Is the whole image? Is just the brain? Is just the tumor area? And we see that when we perform a whole brain or tumor row analysis for that classification, for low-grade or high-grade, we see that the scores are rather the same. So one could argue, well, it doesn't matter whether you use the whole brain information or just the tumor area. But let's run a saliency map on this and let's see what we find. And we found something that we were not expecting. The saliency map, so this is an image that had been skull stripped. We do this in order to facilitate the classification, as we don't want these boxes of the skull interfering with the tumor, as many times it happens, it confuses it. But this generates a gradient in the image between foreground and background. And you can see that the saliency map, that the classifier is picking on this. And that shouldn't happen. It doesn't make sense that a low grade or high grade depends on that border image. So what happens now with our pre-processing? We ask ourselves, why the system is picking on that border? We changed the pre-processing. So we did a normalization based on the brain area instead of the whole image. And you can see now that the saliency map, first, it makes more sense. And secondly, the area of interest, or one of the areas, is the contrast enhanced that is differentiates between low-grade gliomas and high-grade gliomas. It's more localized, as you can see on the T1C image, this part here. Now, the big question is, what happens with performance? Do we gain something, or are we still at the same performance? And we found that the performance actually increases quite a lot. So we moved from 89, 88 that we were before into a 98 performance level. So sometimes interpretability helps us to also find pitfalls in our pipelines to understand what the system might be doing and how we could find ways to solve it. Another example I want to show you, final one, is which sequences are really important when segmenting a brain tumor. what is the system actually looking at, and what are the relations between the subcompartments of this tumor, these sublabels, and those sequences. So 2 years ago, we reported on an approach where we were actually having our sequences being modeled through an RBM, very simple encoder, and we were tracking those parts of the network. And then we have a classifier. In this case, we use a random forest classifier, and we use the feature importance of the random forest classifier to analyze the importance of those deep features. So then the task was, how can we now go back from those deep features into the sequences and also those areas in the images? So I'm going to show you now what I call the barcode type of visualization of interpretability for multi-sequence. So each of the rows corresponds to a sequence. And the bars, the brighter it is, the more important it is, or the amount of importance it has. Features or feature maps that are on the left are more important than those are on the right. So we can see that for the case of classifying the enhancing tumor part of the brain tumor, the T1C sequence is massively the most important. This aligns with the neuroradiologist who looked into the T1C to analyze enhancing tumor. And the T1 sequence, on the other hand, is the least important part of the sequence. Now, at the region-wise analysis, we can see these are the input, T1C, T1, T2, and flare. We see that these are the type of deep features. So this is how the network is seeing that data, one of the most important features. And this actually can also be shown to the MDs and say, do you think that these are the pixels that you would also look at? Do you think this makes sense? So these are nice mechanisms to enhance the interpretability in a very complex multi-sequence scenario. Interpretability can also be used to guide systems, not only to enhance explanations or interpretability itself, but to guide systems. So here, the task is, how do we rank images given a test image and a catalog? I want to find the most similar images and provide a rank. And we want to have those images being of the same class of that test image. And this is the classical example of a radiologist who sees a case and said, I have never seen this before. I need to Google, what could it be? Maybe it's a pleural enlarged cardiomegaly. And then he has to Google, look at the image and say, yeah, it looks similar, might be that. So that's the clinical application. So how we did that, here we see for pleural effusion, these are saliency maps showing the area of interest, aligning with how doctors do it. And now how we train a system to do that, basically we took a CNN classifier network, we ran interpretability maps, and then we fine-tune it. We retune it to use those maps to understand these are the areas of attention for the retrieval system. During testing, we ran our classifier, we create these saliency maps. In this case, we use a type of saliency map called Deep Tailor. And then we ran our fine-tuned CNN classifier. We take the second to last layer as a deep feature. So this is a latent representation of that input. And then we compare those using a simple L2 distance with our catalog, also modeled through those features. And that help us to rank it. As baseline, we use the very popular structural similarity metric that uses the whole image, and a CNN classifier that doesn't use that second fine-tuning I showed you before, and also uses the L2 distance of those latent representations. Let me show you then results. The structural image fails in many cases as it uses the entire image, but doctors, they need to focus on the disease and the condition to say, this image is more similar to the one I'm evaluating. And then by using the proposed interpretability guided approach, we can have a better ranking of images. This also helps with the performance on the disease that this test image has a given label, so we can also evaluate the performance, and we also saw improvements over the other baselines. Let me just to finalize an example of this. You see here, this is the expert ranking, 1, 2, 3, and 4. The red frame means he disagreed with the ground truth that was in that expert dataset. There is an iterative variability, and sometimes they disagree on the label. And you can see the disagreements and the performance for the structural, the pure CNN based, and the interpretability guided retrieval, where we see a more coherent, more aligned to the expert and less errors overall in the classification. Last slide, I have this to suggest you in case you're interested in interpretability as a summary. We report about the challenges, opportunities for this area of research. So with this, I finalize my presentation. I thank you for your attention. I hope you have enjoyed it. Thank you very much.
Yeah, thank you very much for the presentation, and I hope you can hear this.
Yes.
Sorry. I have some applause for you.
Okay, I can hear it.
Okay. So, yeah, there were actually plenty of questions, and this is really, really an important presentation that you have shown, because you are absolutely right that oftentimes we use these deep learning methods, but then we, to some degree, just accept the results, say, oh, wonderful, we have some AUC of, let's say, 0.97, so everything is just great, and we publish our papers. But then we run into the problem that the methods often break on new data sets. So I think what you're doing and what you've been showing here is very, very important for our field, and in particular to try to figure out what's going on and where the weaknesses lie is very important. So I'm really happy that you presented this to us here. And I think this is a very important part of our research, and we should always question whatever kind of result just falls out of a black box model. So I think this is really, really important, and I'm very happy that you were able to show us some of your research here. So we have plenty of questions in the chat. If you have more questions, please type them into the chat, and I will go through them now. And yeah, in the beginning, you were showing some of follow-up studies where you were essentially trying to show to predict the development of a brain cancer. And maybe this is a bit off, but typically, at least in my experience, it's really hard to get these time series data in the first case for a consistent set of patients, because sometimes just patients don't appear again, or somebody forgets to pull the data from the packs and stuff like that. So we had many problems with time series data there. And then also the intervals are at very irregular distances or time intervals. And I'm not sure if you have some tips for people who are working on this, how they can improve on getting better intervals, or also if you have some hints on modeling different time intervals there. What do you think is the best way to tackle this?
Yeah, thanks for the question, Andrea. So Yannick Suter, our PhD student, he suffered a good 1 year just curating the data. So we had that longitudinal brain tumor data set. By the way, it's our interest to release it to the community. So we are going through the paperwork, the ethics, our committees. Wow. To get it out. That's the intention.
That will be a huge service to the community. I'm very sure that will be a popular data set.
So yeah, otherwise, data gets in a hard disk or somewhere, right? And it's really a pity, because the data, it's hundreds of patients between 3 to 5, 6 time points. And the data has been curated because, as you said, it's difficult and it takes time. We naively thought that within 3 to 6 months we would be ready to start analyzing, but that was not possible. There is the whole problem of having the tools to just do many times the spotting of issues. Many times the data from the packs is the raw data. Many times you get duplicates because the patient moved, so they took it again. So you need to go through data and say, oh, here the data is blurred, or it was taken again. Or many times there is a manual problem, an error from the user, mislabeling. So you have a T1C that's actually a T1, and you need to then go through each of the volumes and really curate the data yourself. So I think one of the, I would say, lessons learned from us is the whole quality control. Either have tools or really allocate time budget for that quality control, so that your data doesn't have confounders, doesn't have issues. Then you say, oh, I'm getting just nonsense results. And later you go into results, oh yeah, of course, the data is cropped. I see part of the image only, or the patient moves, so I'm using a very bad image. Yeah.
Absolutely. And I think the data quality and also difference between sites is a huge challenge. So I must say, I really loved how you showed this progression from, the single center study, and then you just select some features with the standard methods. And then you already, when you take data from the same site and you explore on a different set, then you can already get rid of certain confounders and wrong correlations that you identified. So I think this is a very important step, and also that you included the cross-validation there. And then you really go to multi-center. And this is really what you want to be able to deal with in the end, right? Not just from a single site, but you want to be able to process data from several clinics. But this is, of course, a huge effort. So then when looking at the results, and also you investigated the different kinds of features with their biases respective to noise and to different bin sizes and different voxel sizes, I presume, then this was also very interesting. And in particular, with essentially all of the texture features, you've seen that if you change the bin size, they all break down. And do you have an idea how we could harden texture features with respect to different bin sizes, or is it a lost cause?
I'm not really the expert maybe here to talk about like bin optimization. We look into it a little bit. We didn't find good rules. Maybe there are methods we missed, but it was that fine tuning, what's the bin size. And we have seen another paper in radiology talking about it as well, where they simulated data. But as far as I know, there's no like a methodology to say this is the optimum bin size. I don't have an answer to your question, like you should use that method or you should like that, rather than again just sort of testing as a parameter. Yeah.
And is standardizing acquisition protocols an option? Would that help?
Yeah, that helps for sure. The problem is always, I have the impression that even if you have those white papers where people standardize clinical protocols, there will always be that clinical center that doesn't use it, or sort of use a modified version for X reason. Then you want to do your normalization yourself. So we tested so many, standardization preprocessing to normalize the data. We spent time segmenting the gray matter to have a patient-specific reference area. So you would segment away from the tumor and say, okay, let's use these patches as a reference, and we normalized in patient-specific normalization. It didn't make a difference as well. So I would say if your data is standardized already from the acquisition point, then you're lucky. And I see that their clinicians understand, and we need to tell them that what we do is not magic, that the system will digest the data as is, and no problem, just use any protocol. The more they know about it, I think they will be more picky on saying, no, we should use that protocol from that white paper from last year's X journal, right?
And they do have standardized methods where they're very picky about the experimental setup. So this is mainly also related to, because the standard way of assessing images is a radiologist reading the images, and therefore they adjust to their own personal image taste, how they personally perceive the image best.
Yeah.
And this then leads to many different variations in protocols across sites, right?
Yeah. I love your comment because many times maybe the deep learning eye is different and wants to catch something different. Maybe for a human eye would be like, hey, this is not a good quality image. And so that I really like that comment.
Yeah, I think this is also key to understanding the problems that you also, and I think you do that extremely well, that you're in close collaboration with the clinicians and try to understand how they are working. And it's also amazing to see that you have this big drop in performance when you go to the multi-center studies. So you've shown a slide where you can essentially see that you have really good performances in the single center analysis, and then for multi-center you have quite a bit of decrease. Is this also the case with the experts? So if they look at data from different sites, do they also have fewer performance? Do you happen to have data for that?
Not really. They do see differences. So I have worked with colleagues who they are, for example, in lung. Many colleagues, they are very used to the sharp kernel. So when you reconstruct the CT, there is the soft or the sharp kernel, and they fine-tune their eyes to those kernels many times. So there might be a bit of a difference in that protocol, but it's not a game breaker issue. They can still work with the data, and they can, many times they shouldn't do it. They use WhatsApp and they exchange what do you see here, right? And they help each other. Others, they do it with other better systems, but they can actually work with the data. And you see those trials where people merge data from different centers, different vendors, and people can work. And you don't see those performance drops as we saw here.
And this is still a huge problem. So I figured that the loss that is introduced by moving to multi-center data is quite a bit bigger than what you would see in the experts agreements. Or
yeah, much more. Then there is a problem of prospective data and retrospective. So in our case, we had data sets that were challenging because they were old compared to, let's say, today's the best protocol you might find. You do see a difference. But then the question is, if you only design for today method, in 10 years, that method will be again obsolete, will be not robust, right? So you would like a method that even if you are changing the protocol, there is some degree of robustness. So you could imagine it as, now retrospectively, you say, can I handle older data? But then prospectively, can I still use it even if the data changes or the protocol changes?
That's a huge challenge, and sometimes just a software update of the scanner can break the algorithm. So that's pretty interesting to see that these things happen. I must say also the way that you look then at the automatic segmentations and the, let's say, quality or doubt score that you introduced is really cool. And also that you have a trainable doubt score, because this way you can somehow, do you think it incorporates also stuff like artifact level and image quality in the trainable version? Do you think that gets part of the doubt score?
I don't know. That's a very good question. If we could figure out. So eventually you would like to do interpretability on the doubt score, or interpretability on that dice predictor you learned, right? We did some occlusion test in that first preliminary result I show you with the dice predictor to see, my concern is always, I don't want to see pixels in the background, driving the decision. That's always my fear, when I see a saliency map. What drives a good segmentation is difficult because there are also correlations, right, within pixels. And many of the interpretability approaches are very good for classification, but not good for segmentation. So understanding which pixels are driving a good segmentation or a bad segmentation, I think is still a challenge in the community.
Yeah, also it would be interesting to know whether the doubt score can be correlated to a human assessment or expert assessment. That, I mean, they're as clearly images that are harder to assess than images that are pretty clear and we have clear delineations and clear boundaries.
Yeah.
So that would also be interesting if there's correlation to human perception.
Yeah, that's a very good point. I was related note to that. I was wondering, when we train systems and then we test them, we always test them on a batch, and we never look at the complexity of the testing. Because you want a computer to not fail on the super easy cases, right? And you should be more maybe forgiving on the harder cases where also a human might struggle. I know many challenges at MICAI who do patient level analysis rather than sort of calculating an average dice or whatever. They try to do it at the sample level, then rank, and then you compare the ranks. But in many places, we just train, we test on a bunch of cases, and we never look at the complexity there. And I think that would be interesting.
Yeah, do you know of any other methods than just doing a multi-rater assessment of the same case to estimate the hardness of the case?
I saw many years ago, I saw a Nature paper, a machine learning, a Nature method paper that would require a user to say, this is my label. So it was in the case of classification. This is the label, and this is the level of complexity of uncertainty I give to this. And it was not uncertainty. It was, could another rater give the same score as me? I think that was the question. Of course, it's an extra question, more work, but they show good results. And I think that I have seen data sets now, also in the Shakespeare, in this long data set, they introduce an uncertainty. So the user says, it's this class, and when he's not so sure, he gives a -1 score. And they show that when training system with only the certain classes, there is a gain. Now, including the iterator, that would be very interesting. Because it's a measure of complexity, right?
Yes, and you always have these prototypical cases, and you can always show that if you select the prototypical cases, then you always get these wonderful classification rates. But as soon as you mix in the boundary cases, then the classification rate goes down quite a bit. Yeah. So very, very interesting. Also, I mean, for learning with humans, we typically train humans with prototypes and say, look, this is the good example. And then we go ahead and for some reasons, we are able to differentiate the prototypes really well and generalize from that. So I think that is still a very open question for machine learning methods, how to do that in a very well.
I think the whole issue of shortcut learning might be related to that. So the systems, they look at complexity, and the system in a greedy way tries to find the easiest way to solve the problem. And it might find a shortcut, like those examples where, you look at the snow and, okay, it's a husky, right?
Yeah.
And I have this connection, this thought that if you would do it in a more progressive way, as you would train a student, right? You would go into the fundamentals, and then you would progressively fill the gaps of the learning without having shortcuts and saying, yeah, if I just do this, I solve the problem, right? It's the typical student that memorizes and just then, if the question changes a little bit, it's not possible to solve it.
Yeah, but students are also very good at finding shortcuts. So, for example, if you ask the questions in the wrong way, they will be able to figure out things like that very quickly. And so they're also driven by, let's say, good grades and stuff like that. And if they know how to obtain a good grade, they typically do. And we would probably not say that they're stupid when they're doing this.
It's a minimization problem.
No, but they have a kind of world model, or at least a world model of that specific task, and then they understand that it's a meaningful or not meaningful feature. And I think we are kind of missing this in most of our approaches. Yeah, so I really enjoyed also the video that you've been showing about the interpretability and this workshop. This is a very important question to address. And this kind of also relates to, many of the algorithms then need to be applied in clinical practice. And if we look at clinical studies, let's say for new drugs, then we go through these huge efforts to seeing whether the new drug is effective. Do you see a different way other than clinical studies for AI algorithms? So can we make a better approach to that than having to run something similar to clinical studies like in drugs?
There is a whole promise of in silico drug trials and so on, but you move the problem to the whole how to have a realistic in silico simulation. Mm-hmm. I think one before going into the clinical trial, one way is the reproducibility, and that's something that's hard. Imagine that I develop something and I send you an email, Andreas, could you evaluate it? Could you test it for me? So then you have a third party, you have an independent, neutral evaluator of your technology, and you would look for those complicated cases and you would do a completely different evaluation. And then maybe later you have a system, you send it to me and I evaluate it. In biology happens that people try to reproduce methods from other labs, and when they cannot do it, they even write a letter to the editor and they say, we are not able to reproduce the method. Please send us your lab book. We want to see the lab book and how you actually did it, right? I can imagine that maybe that's a step before going into a clinical trial where you say, I ask reference colleagues in the area and they are neutral enough to tell me it works or doesn't, or where it doesn't, before going into the clinics and saying, it was tested by my peers, now let's go into a clinical trial. That's a lot of money, it takes time, and so.
Yeah, I mean, the good thing with software engineering is that we can be very transparent. So we can publish data, we can publish software and so on. And then it may also be a method to increase trustworthiness in results if it can be reproduced and being tested by other colleagues. That's absolutely an important observation. So then here is another question. Okay, this one is labeled as provocative question. Would methods for adaptation use of pre-trained data with few data sets from the new sites be an alternative to robustness to reach the overfitted performances?
Yeah, so how is it called? Few-shot learning. I guess that's the area. Sure, why not? I think it's all about the selection of the data. So if your new domain is well represented by those few samples and your method is able to really capture what's important in that new domain with those few samples, that's the paradise for clinicians, because typically a lot of the things we are doing is supervised. So we need to ask them, you need to annotate data. So if you can tell them just annotate 10 or 50, the system will get ready to the new domain, will get ready to that new machine. That would be really, really, really nice. I'm not an expert in few-shot learning. We are doing some of active learning, trying to remove the need of many samples, so increase learnability or learning rate, by looking at the informativeness of the samples. And cross-domain is, I think, very important. There are interesting studies. My colleague from ETH, Ender Konukoglu, he has some publications on how we could effectively, in a time-effective manner, move from one vendor to the other, to sort of smoothly, nicely, and with few samples. He had an MICAI paper a few years ago about it that I think is very pragmatic and goes in this direction of how do we prepare our methods, because we depend on the vendors. If the vendor changes, we need to start again. We need to do the clinical trial again, and that's yeah, that's time consuming.
Absolutely. There's some exciting things happening in meta learning and future learning, but it's also numerically quite complex because you have then to sample over different tasks and so on. So that makes the problems also a little hard. But it's really exciting field that is opening up right now. One thing that I would like to ask, so I think interpretability is really important. And I was wondering if there is already some results or a perspective in the future that people who deal with the understanding of biological neural networks could actually learn something from us, that we try to understand our deep networks and they have kind of a similar problem. And do you think that there are things that can already be used in such a framework, or what are the main limits that we could transfer such methods?
I have seen approaches that look into that makes the parallel when you learn something new. Your brain is a Christmas tree. You activate many areas. You're trying to find those. You try to connect what you know to connect to the new thing, and in that process, there are many connections across lobes in your brain. When you are driving a car and you've been doing it for 20 years, there is a very very simple connection that uses low energy. Therefore, you can multitask. Right, you're driving and then you are talking to someone, right? So those parallels of, in terms of a network gradient activation, how much gradient activity I have in my network when I'm learning, and when at the end I'm really effective. I have seen those few papers on that concept of making the analogy to the way when we learn something, and what happens in our brain when we are learning something new, and how we use what we learn already to learn the new thing. There is an area in interpretability that the idea is to, given a test sample, you want to know which of the training samples are most important to that new testing sample. And there you want to look into the gradient of your network as a proxy to estimate, these training samples are very important. I wanted to include it in this, but I said it's going to be too long. And basically, it goes in the direction of measuring influential samples to our network or a model. Yeah. And goes into this area of looking at gradient norms, how much gradient that testing sample is generating. Yeah.
Yeah. So thank you very much for your insights. This was really an exciting presentation. I really enjoyed it, and I think you're addressing many really important problems that we have in our field. And I must say, this is really a great talk. So let me applaud again. I hope you can hear it this time better.
Thank you, everyone. Appreciate it.
And yeah, this already concludes the presentation and the questions for today. So thank you very much.
Have a nice day, everyone.
So thanks again to Mauricio. It's a great pleasure to have had you here. You have seen that we had a really vivid discussion already. And of course, this doesn't mean that the discussion is over yet. So if you're interested in continuing the discussion, please engage us in social media. You can also leave comments to this video. And of course, if you're interested in more presentations like this one on state of the art of research in different fields that are close to machine learning and pattern recognition, stay tuned and subscribe us in Beyond the Patterns. Thank you very much for watching and looking forward to any of your comments. Bye bye.